Where are your classmates? Yeah, good morning.
Morning.
Where are your classmates? Relaxing after the assessment? Or is there a company today? Okay, we will move on. Okay, so we were talking about is roll number 22 and 36 here? Excuse me. Roll number 22 and 36?
No, ma'am.
Sundara Srinivasan and Shreyas.
Yes, ma'am, I'm here.
Okay, so you take notes today.
Okay.
And Mohan Kumar and Sriram.
Yes, ma'am.
You get to evaluate today.
Okay, ma'am.
Okay. So let us continue. We were talking about this knowledge-based agent. That is the next one. And this is actually related to reasoning. Okay. So that is what an AI is supposed to basically deal with, reasoning and inferencing. So from this topic onwards, you will try to focus on reasoning aspects. Okay. So so we were in that context we were talking about what is called as an Umpus world, which is a 4x4 grid. Okay, it's a grid of rooms, and you have some percepts. Okay, so the percepts are basically you can perceive stench, which is smell. You can perceive breeze, or you can perceive glitter, or you can perceive a bump, or you can basically hear you can perceive a loud noise, which is a scream. Okay, so the aim is to the agent has to basically start from this grid 1,1 and then try to navigate through this particular grid and then try to get this gold from one of the rooms. Okay, in the process he might enter what is called as a pit, which is going to be absorbing. It's a big hole. You can think of that as a big hole, which is going to basically absorb it completely, or you can basically get eaten by an umpus, which is actually a huge animal. You can think of that as a huge animal or a dinosaur or whatever it is. And in order to identify this dinosaur or this pit, the adjacent squares will basically get a breeze if it is a pit, and it will basically get a stench. Okay. Now, the stench, it has been very clearly mentioned that the diagonal squares will not get it, but the breeze, it is not very much specified that the diagonal squares might be, I mean, will it get it or not is not basically mentioned. So the performance measure, if you do a piece, performance measure of this is basically 1000 to get a gold, or you can basically get eaten by the Oompas. In that case, it is going to be minus 1000. It is a complete loss. You do a -1 per step and -10 for using the arrow. There is of course only one arrow, okay, one arrow, and the moment you hit the Oompas, it's going to basically die. Okay, that is the environment we are talking about here. Now, why is this explained so very in detail? Is your knowledge-based agent and the first representation of knowledge in terms of propositional logic is based upon this particular concept. So that's why we are talking about this too much. So actuators will be what actions will you basically do? You can do a left move, right move, or move forward, or grab the goal. You can release the arrow, and then you can try to shoot the Oompas. That is going to be your actions. So we talked about this characterization last class. Is it fully observable? No, because only whether you can hear a breeze or a smell, only one particular section is known to you. Deterministic, yes, outcomes are exactly specified. And episodic, so it need not be a sequential level of the action. It can basically go random. And is it static? Yes. As of now, we are considering that the Oompas and the pits do not basically move. Discrete, yes, it is defined for discrete points of time. Single agent, yes, you have only one agent to maneuver through the 4x4 grid. So this is the scenario. So here the principal difficulty is the agent is initially ignorant of the configuration, and he is going to have to reason to figure out where the gold is without getting killed. So that is going to be our primary difficulty. So let us try to explore this, and we will try to see what the knowledge-based agent should basically possess. So supposing, say, agent is in 1,1, he doesn't perceive any of the inputs. So you are defining these inputs as a vector consisting of 5 parameters: stench, breeze, glitter, bump, and scream. Okay, stench, breeze, bump, glitter, and screen. So you are talking about some a 5 vector scenario, and initially to start with this parameter is none, so he is not getting it. He is here only, so he is not perceiving anything. So he knows that he can move to the next squares either diagonally, either horizontally, it is move forward or make a 90-degree turn. Okay, so he can basically turn 90 degrees and then move forward, or he can directly move here to this particular square. So that is what is the observation. So what happens is he can move, you can think of this as this is 1,1, this is 1,1, this is 2,1, this is 3,1, and this is 4,1, which is fourth column. This is 4 cross 1, and this is basically 1 cross 1, and this is 2 cross 1. Sorry, 1 cross 2, and this is 2 cross 2. This is 3 cross 3 cross 2, and this is 4 cross 2, and finally this is 4 cross 4. So what happens is this agent tries to he is okay with these two squares because that is what he has sensed. He can try to move this forward. So once he basically moves there, what is the availability? He is smelling stench, which is he observes that there is going to be a smell, a strong smell. He perceives smell, so which is stench is yes, and then the remaining are all no. Okay, so remaining are all no, 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 and a no. So he perceives this, and then he anticipates. Okay, since he perceives that there is a smell, strong smell here, he perceives that anyway, so it's basically if he perceives a smell here, it's not breeze. This is actually stench only. So he perceives a smell. Therefore, these two he anticipates it's going to basically be a Oompas. Okay, possibility of Oompas being in these two squares. So what if he tries to come here? Okay, this is basically done the other way. What if he tries to come to this particular square? He feels breeze. So once he feels breeze, he thinks that yeah, at this particular point there is okay. So at this particular point he feels breeze here. So therefore he anticipates that there could be a pit here um, or even here, okay, but he perceived a stench here. Okay, let us try to reason this. Okay, so he perceived um, um, at square, this is 1 comma 1, this is 2 comma 1, sorry, 1 comma 2, I get confused with the notation. Okay, this is 2 comma 1, this is 2 comma 1, this is 3 comma 1, this is 4 comma 1. Okay, and so he perceives at square, this is first row, this is second row, so this is 1 comma 2, this is 2 comma 2, this is 3 comma 2 and 4 comma 2. Okay, so what he perceives is he has perceived here actually stench. Okay, and he has perceived here breeze. Okay, so this square will not have it, because had this square been a pity one, I mean, when he sensed stench here, he anticipated that the Oompas could be here or here. When he established breeze here, he anticipated that there could be a pit here or here. Okay, here or here. Okay, but he has, if there was a pit here, he should have experienced breeze also here, which was not the case. So he experienced only stench. So he concludes that between these two squares, the possibility of the Oompas is here, and between these two squares, the possibility of the pit is here. Okay, it's just the reverse. I don't want to change the convention, whatever was there in the initial setup. So therefore he tries to move to this particular square. So he comes to, from 1 comma 1, he moves to 2 comma 2. Okay, so that is because he knows that this had he experienced okay, he moves to 2 comma 2 after moving to this particular square, which is after moving to 2 comma 1. So he moves from 1 comma 1 to 2 comma 1, and then he moves to 2 comma 2. Why? Because in between he went to the second row first column. So 1 comma 2, he experienced stench here, and he comes to this 2 comma 1, he experienced breeze here. So based on this conclusion, after experience these two, he moves to 2 comma 2 and assumes that 2 comma 2 will basically be a safe square to move. And then once he comes here, he doesn't experience any he doesn't perceive anything. Okay, so this square is empty, so he doesn't perceive anything. So he basically moves to this square or this square. If he moves to this particular square, he would have experienced breeze. So again, his anticipation could be, once he experienced breeze here, his anticipation could be there could be a pit here, and he has already got a pit here. So this breeze could be because of this pit, or it could be because of this pit, or there could be a possibility of a pit here. So he doesn't move further. He comes back and he again moves here. So now he experiences both breeze as well as stench as well as glitter. So he experiences breeze, which is, this is yes. He experiences breeze and he experiences glitter, and then he does these 0, 0. Okay, so yes, 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 and then there is a no and no, or I can call this as 1 comma 1 comma 0 comma 0. So what happens is he experiences gold also. So he grabs the gold and walks his path back in the same direction as how he had moved forward, and he comes back to the starting position. So this is what it is basically trying to do. So so in each case, the agent draws the conclusion from the available information, and that conclusion is guaranteed to be correct if the available information is correct. Okay, this is very important. So the information is correct, then there is the conclusion will be basically correct. So this is a fundamental property of logical reasoning. So this is what we have to basically, this is I mean, this is how you have to build your process of reasoning and then trying to infer at a later point of time. So here, supposing say you experience a smoke, okay, you experience smoke in a particular situation, you see huge fume, not huge fumes, you see smoke, okay. So once you see smoke, that is your observation, that is your perception, I mean that is what you perceive, okay, you perceive smoke. So once you perceive smoke based on the knowledge based scenario, so you can say that fire causes smoke, okay. You can also say dry ice causes smoke, okay. Uh, but you can also say dry ice causes white smoke, fire causes dark smoke, okay. And if you perceive smoke here, when there is um, of course, if there is no light, you cannot distinguish whether the smoke is going to be dark or not dark. So you can say that fire causes smoke and you perceive smoke here, and there is no smoke without fire could be your conclusion, could be your reasoning. So if this is your knowledge base and if this is what you perceive, okay, based on this knowledge base and this perception, you can conclude that there is going to be no smoke without fire. Therefore, you can say that fire is available in that particular region. Of course, it can be true to some extent, it can be false to some extent. And you can also see that if the environment is going to be, you can also sense, is it going to be a dark environment or is it going to be a bright environment? In a dark environment, you cannot sense the color of the smoke. So, but you can basically smell the smoke. Okay. So, smell can also be used one more criteria as to determine whether there is going to be a fire or not. So, this is what this example also basically briefed you. So, logics is what we are trying to come to. So, logics are formal languages for representing information such that conclusions can basically be drawn. Okay. So, syntax is how the symbols can be put together to form the sentences in the language. That is what is called as a syntax. And semantics is that defines the meaning of a sentence. So, in order to represent this logic, which is represented typically as a formal language, you have to define the syntax and semantics of the particular language. Okay, the syntax will say how the sentences should be formed, and the semantics will basically say what is the meaning of a particular sentence. Now, we are not talking about deriving meaning from a human being, by a human being. We are talking about defining the syntax and semantics so that the machine can basically define the meaningful interpretation. So the sentences should be understandable by the machine. Very important point. We are not talking about you and I referring to this sentence and then saying that, okay, boss, okay, I have a class at 9:30 and so I have to be present at 9:30. Otherwise, this person will mark me absent. That is not, we are not talking about that. Okay, we are talking about scenarios where you are going to make the machine understand this inference and then try to reason it out. Okay. So, example is the language of arithmetic, which says E produces E plus T. You already know this grammar. Okay. So, I'm not talking about grammar here. You already know this is your expression grammar. E produces E plus T. E produces T. T produces T star F and T produces F. This is one way of representing the language as a grammar. Okay. And once you come to this particular point, I know that, and I will also put one more, E is not my start symbol. My start symbol is going to basically be some S, where I will say ID, S produces ID colon equal to E, which means ID is an identifier. Do you guys know this grammar?
Yes, ma'am.
Yes, ma'am.
This is an expression grammar. You know that, right?
Yes,
F produces parenthesis, E close parenthesis, and F produces ID. You know this grammar, isn't it?
Yes, ma'am. We are aware of that.
Okay, okay. So if I this is my grammar, so I know that, yeah, if I have to check whether a particular sentence is obeying the expression assignment statement or not, I have to start deriving from this particular start symbol in order to say it is going to be correct or not correct. Okay, so the language of arithmetic, so I can call that x plus 2 is greater than or equal to y is a sentence. Similarly here, a is equal to b plus c is a sentence. Okay. But whereas a equal to bc plus is not a sentence as far as this grammar is concerned. Okay. As far as this grammar is concerned, a colon equal to bc is not a sentence. Now this colon equal to, I have basically used the Pascal syntax. Let me use C syntax itself. ID equal to E. Okay, this is also ID equal to E. So A is equal to B plus C is my valid sentence. So this is going to be the syntax defining the language of arithmetic. I can also have this as one more sentence type where my grammar will basically involve a relation operator. So I can have the LHS to have an expression. RHS can also be an expression, or RHS can basically be a single variable also, not a problem. So x plus 2 is greater than or equal to y, because this is obeying the syntax of this arithmetic. Therefore, this is going to be a valid sentence. So, and I can also expand this further. X plus 2 greater than or equal to y is true if and only if the number x plus 2 is no less than the number y. So, I am adding more validation, more semantics to this particular sentence, in the sense that I can say x plus 2 greater than or equal to y is true. This sentence, now the first claim here is this is simply a sentence. The second claim here is this is going to be true. This sentence will be true if and only if the number x plus 2 is no less than number y. Now I will map this to whatever example I basically gave you just now. There is no smoke without fire. So I will say that there is smoke here, and I'm inferring that there should be fire. Okay. Now the presence of fire is true if and only if the smoke is very thick. Okay, and I smell something like fire, or I'll see the color of the flame as a bright red flame, which is indicating fire. So if you do that, only I can conclude that this smoke is caused because of fire. Okay, so that could be your conclusion. And x plus 2 is greater than or equal to y is true in a world where x is equal to 7 and y is equal to 1. So this is another example of whatever we have expanded this. And x plus 2 is greater than or equal to y is false in a situation where x is equal to 0 and y is equal to 6. So this is obvious. So these are again expanding or elaborating this particular sentence into two different aspects. So there is a concept called as entailment. Have you heard this word, entailment? Yes or no? Am I audible? Am I there? Are you connected?
Yes, ma'am. You're on.
Yeah,
Okay. Maybe I have my speaker in the low voice or what? Let me check that. It's full. Have you heard this word entailment?
no, ma'am.
Okay, so this is new to you. So entailment means that one thing follows logically from another. Example, just now I told you, smoke causes fire. Sorry, I'm sorry. Fire causes smoke. Okay, fire causes smoke. So I will say that one thing follows logically from another. So smoke will basically follow if there is fire. Again, I am not trying to do inference here. I am simply trying to I'm trying to build my knowledge base. Okay, I'm trying to build my knowledge base based upon this logic. That is, fire causes smoke. So therefore, I can say that smoke logically follows fire. That is called as entailment. And here we say that a knowledge base entails alpha. Okay, so where alpha is a sentence, I can say that knowledge base KB entails the sentence alpha if and only if alpha is true in all worlds where the knowledge base is true. Okay, so you're talking about whether alpha will be true or not true. So knowledge base entails the sentence alpha. Now this knowledge base is going to be containing so many sentences. Okay, and from the set of sentences, remember that you can imagine a say a chat box. Okay, a chat bot. Basically, you can imagine a chat bot and see that what can basically be observed. So you have a knowledge base containing so many sentences, and you will, from those available list of sentences, you try to get one sentence which is going to be true. Okay, so if, and that truth sentence cannot be extracted as just like that, you have to apply some logic, you have to apply some combination to extract that particular sentence. So alpha is the inferred sentence from the knowledge base KB. So it is called as KB entails alpha if and only if alpha is true in all worlds where knowledge base is true. So the same example of smoke, I can probably say fire causes smoke is one sentence in the knowledge base. Then fire will result in thick flames. Okay, that is the next sentence. Then fire will also have some smell. Okay, it could be bad or thick, whatever. And fire causes thick fumes. Okay, thick smoke, and the smokes are basically dark in color. If we have all these inferences, all these sentences in my knowledge base, and supposing I see, okay, I see that there is a thick smoke. Okay, there is a thick smoke which is smelly. Okay, and it is dark in color. Assuming, let us not worry about whether we are talking about daylight or we are talking about the darkness. It is dark in color. I'm able to observe these three parameters. If I do these three parameters, then I can basically definitely confirm. I mean, I can definitely say that this is going to be caused by, there is a fire in this place. So fire is in my place. Fire is in this place is my truth statement alpha. Okay, and that has been inferred by looking at all these possibilities. So this is called as knowledge base entails alpha. So which is called as entailment, where I can say alpha is true if and only if the knowledge base will have only truth sentences. Now if the knowledge base is messy, then I cannot have basically alpha to be correct or incorrect. So here the knowledge base containing the fillies 1 and the reds 1 entails either the fillies 1 or the reds 1. Okay, so both sentences are there. So this can basically be inferred. Okay, x plus y is equal to 4 entails 4 is equal to x plus y. Okay, so this is basically a relation. So entailment is a relationship between sentences which is based upon some kind of a semantics. Okay, now we will also come back to one other jargon called as model. Now this is what you will be expanding in machine learning, where you say you will construct a machine learning model, you construct a machine learning model, etc., etc. That is based upon all these logical statements only, but you don't. I mean, we have actually forgotten AI, and we have forgotten the sentence representation of AI. Everything is now converted to a feature because we are not involved in completely developing a complete AI machine. So we are talking only about in terms of a small section of AI which is actually machine learning. So we are talking about model here. So let us have this jargon also introduced. So logicians typically think everything in terms of models, which are actually structured worlds with respect to which truth can be evaluated. So I have this knowledge base of fire and smoke, etc. So that is my model. That is one model basically. So this is the crux of this particular topic. We say M is a model of a sentence alpha if alpha is true in M. Okay, now already we said that knowledge base is going to be entailing alpha. Alpha entails knowledge base. So alpha will be true only if The knowledge base contains all truth sentences, and from that I can infer what is alpha. Now we say that M is a model of a sentence alpha if alpha is true in M. So this model is going to be your knowledge base. That is what we are representing here. So M of alpha is a set of all models of alpha, and the knowledge base will entails alpha if and only if the model of knowledge base is a subset of model of alpha. So alpha is something more. Okay. So this is the small knowledge base. So from that you are trying to infer this alpha here. Alpha is somewhere present in this outer box. So I can say that the model of the knowledge base will be a subset of model of alpha. So the example, knowledge base will have Phillies 1 and Yankees 1. So alpha will basically contain only Phillies 1. So this could be a subset of the alpha. And let us try to do this with respect to the Umpus world, whatever we are talking about, whatever we have observed as model, as observed as knowledge base. Let us let us try to get this particular situation with respect to the context of Umpus world, because we have just now seen that example. So assuming that you are detecting 1,1 here and you are moving right, so you sense breeze here. So breeze is in 2,1, and consider the possible models for knowledge base, assuming only pits. Okay. So that's why I said. So here we already said, I already said, when you experience breeze, nowhere in the book or any material says whether the diagonal will have a pit or not. But here it is assuming that the diagonal can have a pit, and because you have not moved here. Okay, so there is a breeze here, so you can basically think of a pit here, here, or here. It could be even here, but I have not moved there also. Assuming that these three have not been explored. Okay, so I have an typically it's here and here only. This is just an extra stuff. If this is an extra stuff, I should have basically explored here also, but that is not experienced. So assuming that you have 3 Boolean choices to make 1, 2, 3. So you end up with having 8 possible combinations of where the pit is going to be available. So this 8 possible models can be, 8 possible combinations can be thought of as 8 different models. So you experience breeze here. So your possibilities are 0, 0, 1, 0, 1, 0, 0, 1, 1, okay, 1, 0, 0, 100, then 101, 110, 111, or 000. But 000 is, this is not a valid argument, because you have experienced breeze here. So one of these two, okay, should definitely have a pit. Okay, so therefore that is what we will be focusing on at a later point of time. So there are these possible models. So 001 means breeze is experienced here. There is a pit here. This is 010. Pit is here. Pit is in both positions. That's also a possibility. Pit in all the 3 positions. I do not know, because if there is a pit here, I should have experienced a breeze here also. So that is not a valid argument. So you have all possible models. There are 8 possible models, but okay, what is the actual possibilities are only these 3 are the possibilities. Why only these 3 are the possibilities? This is obvious. I have a breeze here. Adjacent square can have, adjacent square can have. So that is these 2. Both can have. That is this particular third argument. This is not a possibility because you have experienced breeze here. This is not a possibility also because you have not experienced breeze here. Okay. This is not a possibility again because you have not experienced breeze here. So wherever there is a 1 in the second row first column, it is completely ruled out because you have not experienced breeze in the first row first column. So therefore the second row first column is ruled out, and no pit is also ruled out because you have experienced breeze here. Only these are the valid observations. Okay, so that could be your conclusion. So in that case, these are the valid observations. There is no pit in 1, 2. Okay, alpha 1 is equal to, there is no pit in 1, 2. What is 1, 2? first column, second row. Okay, there is no pit in 1 comma 2 is your conclusion. That is why we have ruled out all these scenarios. Okay, first column, second row. We have ruled out all these scenarios because you have not experienced a breeze at 1 comma 1. So therefore, the alpha 1, which is going to be a sentence to prove truthfulness, there is no pit in 1 comma 2 is your conclusion. Knowledge base will entail alpha, and this is proved by model checking. So you can try to do all these combinations as alpha 1. So alpha 1 says there is no pit in 1 comma 2. So that will comprise of these 4 possibilities. And out of that, the knowledge base will have only this particular 3 because this is also not going to be a valid combination. So the knowledge base contains all possibilities of alpha 1. I mean, the model of alpha 1 contains whatever alpha 1 is true. Out of those alpha 1, whatever is going to be used for making your inference, that will be contained in this knowledge base. So that is going to be your representation of KB versus alpha. So we said knowledge base consists of a subset of alpha. Example is this one. So you have 8 possible combinations. Out of the 8 possible, 4 possibilities are definitely ruled out. Okay. What is now reminding us, your conclusion is there is no pit in 1 comma 2. So there is no pit in 1 comma 2 is your conclusion. So alpha 1 consists of the 4 possible models where there is no pit in 1 comma 2. Out of that, you have experienced breeze. Based upon that, you are concluding for a pit in some particular position. After including there is no pit in 1 comma 2, you are saying that these 3 components consist of your knowledge base. The 4 components consist of your truthful statement for alpha 1. Okay, so depending upon whatever is going to be observing, this is how you basically check. Okay. So this is your Umpus world rules plus observations. These are 3 valid arguments. So there is no pit in 2 comma 2. Okay, there is no pit in 2 comma 2 means then it will consist of alpha 2 will basically vary, and the knowledge base will entail alpha 2 or not. That is not going to be true because if there is a breeze here, then this will basically, this should contain alpha 2. So your knowledge base is not going to be part of this alpha 2. So it will be different. So you need to be very specific in constructing what is going to be your model of alpha, model of your entailed sentence alpha. Okay, and then construct your concept accordingly. Okay, so there is no pit in 2 comma 2. So this is included, this is included, this is definitely not included, this is not included. This is not included, this is included also, this is included also, but you have experienced breeze here. So your possibilities are, it could be having a pit here or here. Okay, so then you can try to conclude, but where is the pit actually? Pit is here, it is not including that. So this cannot be called as a complete knowledge base, doesn't entail alpha here in this particular example. So you need to select your model and alpha accordingly in order to make some inferences and reasoning. So we have come to inference here actually. Inference is a procedure which allows new sentences to be derived from a knowledge base. Okay. So you can think of entailment and inferencing slightly different. So set up all consequences of a knowledge base as a haystack. Okay. And alpha as the needle. So you're talking about checking, finding a needle in a haystack. Okay, so entailment is like the needle being in the haystack. Inference is like finding it. Okay, so entailment is you know that there is a needle available. Okay, so it's available. So you are trying to infer by going through all the procedures in order to find out where this particular new sentence is available. So what can I draw from this from these set of sentences? There are sentences, there is some truth available. From this truth and the set of sentences, what can I basically get? Okay, that is going to be called as inferencing. So some rules and properties of inferences and entailment. So we can say that knowledge base will entail sentence, will infer alpha. Sentence alpha can be derived from knowledge by inference procedure I. Okay, and soundness and completeness are two characteristics of inferences. So you can call that an inference I is a procedure I is sound if whenever knowledge base uh, derives alpha, it is also true that knowledge base entails alpha. So derives alpha means what? You are getting an inference statement from this knowledge base. In that scenario, when you can get that, indirectly this alpha is available in the knowledge base. That is, alpha entails alpha, alpha entails knowledge base is also going to be part of your game. So that knowledge base is called as sound knowledge base. And there's something called as a completeness. This procedure I is complete if whenever alpha entails knowledge base, it is also true that knowledge base will entail alpha. It is something like an if and only if statement. So both are going to be true. Okay. So you have to define a logic for doing this inferencing, which is very expressive to say almost anything of interest, and you have sound and complete inference procedure for the same. So for this inference procedure only, we have to go in for two inferencing algorithm called as forward chaining and backward chaining algorithm. So these two will be done with respect to first order logic. So we'll first introduce propositional logic. Some certain things you already know, you have done as part of the discrete maths course. So let us see that also. So you will be in a position to find out, you will be in a position to answer any question whose answer follows from what is known by the knowledge base. So you have the knowledge base, you have basically a model comprising this knowledge base. So whether you expand the knowledge base completely or not, you should basically be, your complete scenario can also be your knowledge base. So that is, this can be the knowledge base as well as alpha, because it's a subset of M of KB is a subset of M of alpha. So this itself could be the knowledge base. So you will have to get one sentence alpha inferred from this knowledge base, which is going to be a task, and you will do some algorithm for the same. In order to do that, you need to first be expressive enough to have syntax and semantics defined for the knowledge base. So sentences will entail sentence. Sentences are defined using semantics, and sentences will be also used on the semantics, and the aspects of the real world will basically follow the aspects of the real world. So this is the representation, this is the world. So this is the actual world, and for that particular aspect you will be representing in a format which is understandable by the machine. Okay, so this is what is the machine component, this is the actual real world component. Okay, so you can say that there is an inference procedure whose conclusions are guaranteed to be true in any world where the premises are true. So this is what we said in the beginning of the statement. KB entails alpha. As the knowledge base is true in the real world, then any sentence alpha derived from KB by a sound inference procedure. I can even add one more word, which is called a sound complete. When I say sound complete is, when I say complete, sound and complete basically are mutual. Okay, so if I say sound and sound inference procedure, I'm also including here a sound complete inference procedure, just to be on the clarity, just to be double clear on what we are intending to get it. It's also true in the real world. So propositional logic, this is a very simple logic here. How many of you remember propositional logic? You have done that, no, in discrete maths?
Yeah, we remember the basics, ma'am.
You remember the basics?
Yes, ma'am.
Yes, ma'am.
Okay. Fine. Okay. Let us just go through this real quick. Maybe I think I have to stop after this topic. Anyway, so supposing P1 and P2 are atomic sentences. Atomic sentences are basic sentences. Okay. that is based upon your knowledge base. If it contains atomic sentences, it will be easier for you to do your inferencing task. So these are simple scenarios. If S is a sentence, not S will also be a sentence. If S1 and S2 are sentences, then S1 and S2 will also be a sentence. Or of them will also be a sentence. S1 implies S2 and S1 if and only if S2. Okay, so this is an if then, this is an if and only if sentence. So all these will basically be sentences also. So you know probably this, not supposing not S is true if and only if S is false, S1 and S2 is true if both are true, S1 or S2 is true if one of them is true, S1 implies S2 is true if and only if S1 is false or S2 is true. Okay, so this is very important. S1 is true and S2 is false. So this is going to be your situation. And S1 double implies S2 means both should basically be true. S1 should imply S2 and S2 should imply S1 is true. So this is your rules. The same truth table connective is here. So P implies Q. These two everybody knows. This is very direct. P implies Q. P is false means Q should also be false. P is false and Q is true. That is fine. But P is true means Q should be necessarily true. Else this is going to be false. So this is the only variation. And here if both are false, it is true. If both are true, it is true. If one of them is true, then it's going to be false. So this is going to be your connective. So we'll come back to this in the next class. Based upon that, we will try to do an inferencing and we will have some algorithm for the same. Okay, so we will continue this in the next class. Okay, so we will see on Monday this particular topic. You submit the second assignment if you have not already done so. I saw some 2 or 3 submissions. Submit that by, it's due tomorrow, right?
Yes, ma'am.
Okay, fine. Okay, thanks. We'll close it today. We'll come back tomorrow. Sorry, Monday.
Okay, ma'am.
Thanks. Yeah.
Thank you, ma'am.
Thank you,
Yeah.
ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.